Hi, welcome to video 5 in my series on Introductory Data Science with R. I'm your host, Dave Langer. The subject of today's video is going to be cross-validation. And cross-validation is arguably maybe the single most important concept to learn and leverage in your data science work when you're trying to apply machine learning algorithms to a data science problem. So at base, cross-validation is a way for you to get two things. One, to maximize the value of your limited training data, and two, to provide you a way to estimate how accurate or how good your model is against unseen data. And what we're going to do is talk about that today, and I'll provide you some resources on YouTube so that you can dive in on the topic further using the Titanic competition as our vehicle. So where we left off last time, and you'll see here, we're in the video 5 section of the code file, is exactly where video 4 ended, which was, here, let me just clear the console real quick here, is we did some exploratory modeling, and we found that when we trained a bunch of random forest models with various types of features that we investigated in the earlier parts of the series, that our fifth attempt, or RF.5, which is the fifth random forest we trained, actually provided us the best results. And we did some plots in video 4 of the variable importance for each of these random forests that we trained. And what we found was that the best combination of features that we have engineered to date were our title feature, our p-class feature, and our family.size feature represented as a factor object, and that produced a random forest with a error estimate of 18.41%. And when we went back and looked at the Kaggle leaderboard, we said, look, if we had the corresponding accuracy rate, because that's how the Kaggle competition is judged, that random forest estimates that our error was going to be, our accuracy was going to be 81.59%, which was actually a top 10% score at the time of the last recording. And we said, hey, you know what? If that error estimate that the random forest algorithm is giving us is accurate, that's pretty good. That's a really good model, especially considering the fact we're only using 3 small features here. Well, the problem is that, as I talked about, is that the random forest algorithm is great because it has lots of really cool features, not the least of which is that it can provide you an estimate of your error rate. However, in practice, that's really going to vary quite a bit, and there's always the potential for overfitting, and you've heard me mention that a number of times, but overfitting is really the bane of applied predictive modeling / machine learning in the data science realm, right? It's very, very easy to just engineer tons of features and use great algorithms and create models that you think are super awesome. And then when they get into production and and they are presented with unseen data, they're just not very good. So cross-validation is the single most important thing you can do for creating a methodology that allows you to actually estimate what your error rate is as you're doing your iterative data analysis, feature engineering, model training, rinse, repeat over and over and over again. So the good news is that in the Kaggle competition, we have a built-in mechanism to explore this topic further. First and foremost, Kaggle competitions usually give you both a training set, which usually has the labels or the value you want to predict if you're using a regression problem in the competition, as well as a test set, which is unseen data with no labels. And your goal is to use the training data, build a model like we did here with RF5, using the training data, and then leverage that model to create predictions for the test set. And then you can submit those to the Kaggle website, and they'll give you a score. Now, what's great is, from a cross-validation perspective, is that gives you a way of giving yourself a sanity check to say, look, how accurate are my error estimations, my training data, in my iterative cycle of development, versus what the real values are. And that's good because you're going to want to, at some point, shy away from judging your model's predictive power based on just the leaderboard. And let me give you an example why. In every single competition that I've ever participated in Kaggle, I always end up at a higher rank in the stack than the leaderboard would suggest. And the reason for that is because I'm obsessive about not overfitting. You'll find some folks, and this is too bad really, who will submit many models, and what they're trying to do is get the highest score possible on the leaderboard. Now the problem is that Kaggle always keeps it in another set of data that they use to finally judge the competition totally secret. So really there's actually 3 chunks of data that happen in a Kaggle competition, and this was the same thing in the Netflix prize. It's very commonly done, which is Kaggle will give you the training data, as we talked about, and the test data. And then they'll actually have a final set that they keep totally hidden from you. And then that's what's actually used to judge how well you did. So if you have a tendency to build your models to do really awesome on the test data as scored by the leaderboard in Kaggle, and you don't make sure that you're really trying not to overfit, you will do very well on the leaderboard, and then you will drop in the final analysis of all the teams that are competing. And that happens over and over and over again, that people drop, and sometimes people drop huge amounts, hundreds and hundreds of ranks, because they've overfit to the test set. So we really don't want to do that. So what we want to do early on in a Kaggle competition, for example, and you can do this in your own work as well, if you'd like, with business data, is to establish a cross-validation methodology that gives you a fairly accurate estimate of your error rate on unseen data. So that way you just concentrate on your cross-validation, your feature engineering there, and you don't do much with the test set, generally speaking. Okay, so enough theory. Let's go ahead and do a submission to Kaggle real quick and validate that our estimation of our error rate, which here is, our accuracy of 81.59% actually matches reality. So what I can do here is pull out of the data.combine data frame, which is both our training and test data, the last 418 rows, which would be indexes 892 through 1309. Those correspond to the original test set. You can see over here, test 418 observations. And we only want 3 features or 3 columns out of the data, right, that correspond to what we trained our RF5 on, which are title, p-class, and family size. So that's what we did here. And we're going to cram that into a new data frame called test.submit.dataframe. Let's run that code. And you can see here, test.submit.df gives me 418 observations, which is good because it's the same number of tests, so that's a good check. And then we can use that to make a prediction. So how you make predictions, generally speaking, using R is use the predict function. So as usual, don't hesitate to use the help system. And one thing you'll notice in the IntelliSense that pops up in later versions of the R Studio environment is that there are actually many predicts functions here. Right? Here's one for something called AVNetNet, which is aggregate several neural network models. And if you scroll down, there will be one for random forest as well. Let me find it here. Yeah, there it is right here. Now what these are overloaded functions. R implements an object system where you can call generic functions, and at runtime it will say, hey, wait a second, you're trying to call predict on random forest. Let me actually invoke the predict.randomForest function for you instead. So that's kind of handy. So you just use predict, and you can use the help system, and it talks all about it, and it provides even more examples, right, of overloaded functions here. But what we're doing in this line of code is saying, look, make some predictions using the RF5 object that we created from our training of a random forest. Use the test.submit.df data frame as the input. create those predictions, and then store them in this variable that I've called rf.5.preds. So we just run that line of code. And you can see here's a new variable called rf5preds with factors of 2 levels of 0 and 1, right? Perished and survived. Great. That's exactly what we would expect. Next, we can create a table or run a table command on that just to get some idea of how our preds distributed. And we can see here, hey, look, out of the 418 records in total, we predicted that 160 would survive. So what, more than a third, maybe less than 40%, so somewhere in there, between 33 and 40% of folks survived, and then the rest perished. So, okay, great. Now that's our predictions. But we're not done yet, because Kaggle usually requires a CSV file as its submission format. So what we need to do is transform our predictions into a CSV using R code, and that's actually really, really simple. It's one of the reasons why I like R so much. As with most things in R, it all starts with a data frame. So we're going to create a new data frame, and we're going to give it some structure. And specifically, we're going to give it 2 columns, one called passenger ID and one called survived. And then we're going to populate the passenger ID column with just numbers ranging from 892 to 1309. And once again, if you're not familiar with the rep function, you can just !rep, and it says replicate elements. Sweet. So this basically says, look, I'm giving it a range, and it's basically going to spit out the numbers 892, 893, 894, etc., all the way up to 1309. And then in the survived column, we're just going to give it the preds, and it's going to give us 0 or 1. And if we go over to the Kaggle website, we'll see that this data frame matches the structure that it's expecting. So if you go over here to the Titanic competition on the Kaggle site, you go to the data page and you look at one of the sample CSVs. Here's the gender model one. I can bring that up here in Word, Excel. Whoops. Maybe not. Let's click it. Okay, there it is. And you can see here, sure enough, passenger ID, survived, 892, so on and so forth, and survived, right? Great. So we need to mimic that structure. And what we're doing is in R, we're creating a data frame that mimics that structure and then cramming it into a new variable called submit.df. So if we run that line of code, we have 418 observations of 2 variables. We can click on that in the UI and say, okay, great. Yep, it's exactly what I expected. Cool. Got a data frame in the right format. Now I just invoke the write.csv function. Once again, don't be afraid to use the help system. Let me maximize this to get more screen real estate. And you can see here that it's a part of a general family of functions. Now it's pretty simple, right? You pass in a write CSV the data frame, and it's automatically going to convert the DF into a CSV because they're both basically tabular representations of data. So it's very easy to convert. You tell it what kind of file, or excuse me, the file name that you would like to use, and by default it's going to write to the current working directory that you've got set up in your R environment. So wherever you set up your current working directory, it's going to write out a file called whatever you call it. Now what you see here is a naming convention that I typically use. You can name your files whatever you want, but I typically find it's useful to provide some metadata in my submission file names when I'm doing Kaggle competitions because you end up having a lot of them. So basically what this does is this naming convention says, look, it's a random forest submission, and I did this one yesterday at the time of this recording on Valentine's Day. Yes, I know. Don't get me started. 2016, February 14th, and this was my first submission of the day because most competitions allow you to submit multiple times per day. And what this allows me to do is that if I'm doing a bunch of random forest submissions across a number of days, this will automatically sort them in order based on not only the date in question but also what submission I did. And that's just what I do. You don't have to do that, but if you're wondering, that's what this funky naming convention is. Now this is important because this parameter here is you don't want any row names Basically what it'll do, if you leave this off, the default value is true, as you can see over here in the help system, and it's going to add an additional column and it's going to put row names in there, and you don't want that. It's extraneous data, so never forget to use row names equal false. And if we run this, actually, you know what? So this is the 15th. So let's just change this real quick, the 15th, and we'll just run this. And it writes out a file into my file system. Now I'm not actually going to go through doing this submission because that's ridiculously easy and it's not really worth our time to do that. But as you saw, I ran this code yesterday to get a baseline, and the submission scores 79,426. But our OOB estimate predict that we would get 0.8159, or look, this model actually was actually 79.426% accurate when our random forest predicted that we would be 81.59% accurate. Now, if you go check the Kaggle leaderboard, this is not a superlative score. This will put you somewhere in the 50%. So this is indicative of what I was talking about earlier, which is we really need to find a way to say, look, when we're training our models and doing things, how do we know that we can trust that these things are accurate? Now this isn't too big of a difference, right? It's about what, 2% different, and generally speaking, that's not bad. The only problem is that if you can't get your cross-validation closer and closer to your actuals, you always run the risk of never knowing for sure if your increases in accuracy because of your feature and your engineering efforts are because of you actually building a better model, or you're just tending to overfit the data set. So it behooves you to try and get these numbers, if possible, to get as close as you can. And how you do that is by using cross-validation. It's the single best way to do it. I mean, it's almost the de facto standard on Kaggle. There are other methodologies you could use, but in general, you can't really go wrong with cross-validation. It is kind of the de facto standard. So before we get into how you do cross-validation, let's find some resources to bootstrap you into the concept a little bit more. So, as usual, YouTube to the rescue. So, there are many right? I just type in cross-validation comes up, right? There are many resources on YouTube on cross-validations. The question is, what are some of the best ones? To be honest with you, you can never have too much information. If you watch multiple videos on cross-validation from different sources, it's probably not a bad idea because it's that important. But if you just want to bootstrap your way in ASAP, look up Jeff Leake. And you can see I've already doing some searches previously in preparation of this video, which are why some of them are highlighted. So Jeff Leake is a member of the faculty at Johns Hopkins, and he actually does a number of courses on Coursera. And in fact, early on, maybe 3 years ago or so, I took a data analysis course from him on Coursera, and it's really quite good. So just type in Jeff Leake. Pick him because that'll take you to his main page here, and you can see he's got 4,600 subscribers, so wow, he must be a good dude. If you scroll down, there'll be a Coursera data analysis listing. Just click on that, and that gives you a bunch of videos. Now you'll see here that I've already watched 2, and these are the 2 I'm going to recommend. What I would recommend doing first is start with the video called Prediction Study Design, right? And let me just go ahead and pause that. You could watch the whole thing. I would hardly suggest that, not surprisingly, but if you didn't really want to watch the whole thing for whatever reason, you can get in about 1750 here-ish. So let's go 1740 just to be safe.
Concordance. So concordance is
and I'm going to go ahead and pause that. And this is when he starts talking about maybe it's like 1752, yeah, it's 17, like right around here, right? 1750, 1755. This is when he starts talking about the holdout sets and things like that. This right here is the example from the Netflix competition, right? And Kaggle uses exactly the same setup for the most part, except for they don't use the probe, right? They give you the training set, they give you a test set, and then you can think of the quiz set as the one they hold out and actually finally judge the competition on. So you can watch the rest of the video. It's only about 4 minutes. And then once you're done with that, you can actually watch the dedicated cross-validation video. Excuse me. And this one's good. But I would recommend watching the last 4 minutes of the first video because he kind of jumps in, assuming that you've already know some of the stuff that he talks about. So altogether, it's about 18, 19 minutes worth of content. So I would heartily recommend jumping into that because that gives you a baseline for it. And then if you want to watch more videos on YouTube, knock yourself out. More knowledge never can hurt in data science. Had to learn that the hard way over time. Okay, great. Now getting back to our code, right? We've done our submission and we know, oh, well, it's not so bad, but it's not so great either. We've got a difference in expectation between what just running a random forest on the full training set would estimate our error to be and what our actual errors are on the test set. So we've got some R help to the rescue. So let me scroll down here. Okay. So the first thing I want to talk about is the carrot package. If you're not familiar with the carrot package, you need to be. Carrot is your friend when it comes to building machine learning models as part of your data science work. It has so much goodness in it, I can't even begin to describe it to you. So what you're going to want to do if you don't have it installed on your environment is to install it. And it's pretty easy in RStudio. We've done this before. You just go to Packages, you go to Install, type in carrot. And usually what will happen, well, see, I'm configuring my repositories right now, but the drop-down list will show up. It'll segment down to carrot because obviously as you type in more characters in this box, the drop-down shrinks down, narrows down, and you can just install it. Carrot is super awesome. Now this is something we haven't, I don't think I've done this before, but maybe I have. I'll just do it again. So using this syntax here, you can actually gain help at the package level. So we can type help package equals carrot in quotes, and it pulls up the main help for the carrot package in general, which stands for classification and regression training. So as you can see here, there are lots and lots of functions, lots and lots of goodness in the carrot package. And to be frank, carrot is so good, I found it so useful myself, that when I mentor folks who are interested in getting started in data science and for some reason decide to value my opinion on that, I tell them to pick R usually first over Python. And some folks may consider that blasphemy, but my experience has been is that, as I may have mentioned before, that the R language has so much going for it that it's really amenable to folks starting out. Now, if you're a dyed-in-the-wool programmer, you may find Python easier to adopt just because it looks more familiar from a programming language perspective. However, there are a number of things in Python that are just quite frankly more difficult to do than in R. And when you're really ramping on the core concepts of data science, I would say, look, you know what? That impedance mismatch is just too much to overcome, so why bother? Not only is Carrot awesome just because it provides you so much good stuff, there is probably the single best book on applied machine learning is written by the Carrot authors. And out of all the books that I've got on machine learning and in data mining, and I've probably got 30 books that I've accumulated over the years. I haven't necessarily read them all cover to cover, obviously, but a lot of them I have. And this is, if you were going to, I could honestly say, if you were going to buy one book on how to do predictive modeling and machine learning well, this is the book, and it's called Applied Predictive Modeling. And it's authored by the two primary contributors to the Carrot package. And this book is sweet. It is super sweet. It gives you so much information about everything that you need to know, including our code samples. So this book, if you're going to buy one book, buy it. Now, I own it both in physical form as well as Kindle. So unless they've radically improved the Kindle edition, I tell people do not buy the Kindle edition. Buy the hardcover first. I have both mainly because I use the Kindle for reference. But when I read and want to study something or restudy something, I go back to the hardcover because the Kindle translation isn't very good, quite frankly. But Carrot, awesome. This book, awesome. Nothing but goodness. If you search, this particular title across all the Kaggle forums, you'll find lots of posts that talk about how important it is to read to help you get bootstrapped in. So, enough of the praise for Carrot. Oh, there's also a really, really good website for it as well. So you can just Google it and you can see the Carrot package here. Great website. Lots of help. However, again, I'd buy the book. I'm just saying, it's great. Okay, enough effusive praise. Such a fanboy. Okay, so Carrot provides a bunch of algorithms that make various activities easier, cross-validation being one of them. Now, the problem with cross-validation is that it is quite intensive compute-wise. So, as you probably learned if you watch the Jeff Leake videos, if you do what's known as tenfold cross-validation, what you're basically doing is splitting your data into 10 logical chunks, your training data into 10 logical chunks. And then you're iteratively grabbing one of the chunks, holding that out as the test set, and then training the other 9 chunks with your algorithm, and then running predictions against the one that you held out, and getting a result set of how accurate your model is or how good your predictions are. And then what you do is you do this all over again a total of 10 times until every chunk has been used as a holdout. And what that allows you to do is use all of your data to train models and then get some idea of what it would look like accuracy-wise on totally unseen data, because what you do is you average your error rate or your accuracy rate against all 10 runs against, you average them all and that gives you your overall value. Now what that means though is that you're basically training your model 10 times. So if you create a random forest with 1,000 trees, that means you're actually building 10,000 trees for one cross-validation run. Furthermore, research has shown that repeated cross-validation is actually better. And there's a book, a really good data mining book, that essentially states that you should do your default position for cross-validation should be do tenfold CV repeated 10 times. Now, once again, if you think of building 1,000 trees, that actually means I'm building 100,000 trees because I'm building 10 times 10 times 1,000 or 100,000 trees. So given where we're at right now, that our data set is extremely small and we don't have many features, it's not really a problem. But as you might imagine, this becomes computationally expensive, like in a exponential or geometric rate. The bigger your data set, the more features you have, the more complicated the algorithm you use, maybe like a deep neural network, for example. I mean, this gets to be very, very super intensive. Now, the good news is that Carrot is smart enough to know that if you register a package and invoke it that allows you to use multiple cores, you can actually get this work done in parallel. So by default, R is a single-threaded memory-bound environment. It runs on one thread and it loads everything into memory, and that's just the way it works. Now that provides a lot of limitations. And over time, there have been number of packages built to get past our scalability limitations as the scale of data gets bigger and bigger. Because you got to remember that R was originally built for scientist folks and statisticians, and typically they're working on relatively small data sets, right? This was really R was designed and built before the age of Google and LinkedIn and Facebook and Amazon and what have you, right? And Bing or whatever. So that's why we're also going to use the DeuceNo package. So once again, if you want to install it, you would go to packages, install, and you would type in DeuceNo, and you can see now that my dropdown is working, right? DeuceNo. Now there are many packages that do this. I use DeuceNo rather than other packages because, as we'll see later, DeuceNo works on both Macintosh and Windows. It should work on Linux, but I've never actually tried it on a Linux VM. But I use DeuceNo all the time. And what this allows me to do is essentially parallelize my work for carrots. So, because when I'm training 100,000 trees, let's say, it would be nice to be able to use all the cores on my machine if I've got a multi-core machine. Okay, so great. So the first thing that we need to do is, if we're going to do 10-fold cross-validation repeated 10 times, which is the default place to start. You should always start there if you don't know any better. If you know more, if you have more data, then you may change your methodology a little bit, but in general, 10-fold cross-validation repeated 10 times, very good place to start. That means we're going to need 100 folds, right? We're going to need 100 distinct slices of the data in such a way that we can use those over and over again. Because what we want to do is we can't use the same 10 folds 10 different times because this is going to give us the same result. We actually need to randomize it. So we actually need 100 folds, 10 collections of 10 folds, where each ideally of the 10 groups of folds are different from each other. Okay, sounds really complicated, but as usual, carrot to the rescue. So let's go ahead and pull up the help for create multifolds. Okay, so create multifolds is part of a family of functions for data splitting operations in Caret, as you can see here, right? Now, what's really super awesome about the Caret functions is not only can they handle all the randomization for you, they can also do something called stratification. And stratification is important because, as we know in the Titanic data set, more people died than survived. Quite a few more people died than survived. And what we also know is that in aggregate, while it's not super imbalanced, it was like roughly 1/3 of folks perished and 2/3 of folks perished and 1/3 of folks survived. We know actually their proportions got worse based on P class. So for example, males in third class died, unfortunately, at a much, much higher rate. So what that means is that we could potentially slice this data up into 100 different folds, right? 10 groups of 10 folds. And if we just did it randomly, we could potentially get some folds that were all perished. Everyone just perished. So that means that basically every model, that data is just not skewed very well. So what we should do is stratify, which means, look, take the proportion of your label in aggregate. So let's say it's roughly, in our case here, 1/3 survived and 2/3 perished, and make sure that every fold that's randomly generated has that same proportion, approximately. And this is great, right? Because we don't have to worry about it. So Caret takes care of it for us automatically. So as we've seen before, anytime we're talking about any sort of randomization in R, if we want to make sure that we can get reproducibility, we need to set the random seed. So that's make sure that we always start the random algorithm at the same point every time. And we say, okay, set a seed, call the create multifolds. We provided the label, right, which is our RF label. That's what we trained RF5 with. So we can double check that real quick. Go to RF5 here. And we can say, yep, our Ys or our labels was this RF label thing. And what that allows the Caret function to do is say, okay, great, I can do two things. I can figure out the proportion of the labels, so I can make sure the stratification works correctly. And it also gives me the indexing as well, right? Because what I'll do is I'll just pull back a list of indexes. This is what create multifolds returns, is just a bunch of indexes into your training set. That's all it does, because why give you the full records? That's just a bunch of data that you'll have to store in memory that's redundant. If we just give you the indexes, you can pull it directly from the training set. It's great. So K says how many folds, right? And how many times. So what we're saying is, look, we want 10 folds, and we want 10 groups. So that'll give us 100 folds. And if we run this, we can see here, CV10 folds is a list of 100, which is exactly what we'd expect. But just to be clear, let's check the stratification. So this is RF label all up. If we run the table here, we can say, okay, look, you know what? 342, 549, great. Let's just go ahead and run a quick math calculation to say what proportion. So approximately 62.2923, 62.3% of, the amount of people who perished is, 62.3% of all those who did not survive, right? So what this code says is, look, grab the 33rd entry in this list of 100 from the CV10 folds. Right, and that's basically a series of indexes. Index that into the RF label, and then tell me what that is. So what we should see is a smaller number, right? Because each fold is only going to be 1/10 the size, right, in general. And we can see here that the results are essentially the same. So the proportions are basically the same, right? So this fold, the 33rd fold, and I just chose that number at random, produces a bunch of indexes, brings me back indexes, it brings me back the indexes, and I go ahead and slice the RF label, and then I just calculate what the percentages, and we can see here that compared all up, the relative percentages are the same, so we're stratified. Okay. Now that's a bit complicated. The whole point of this is just to basically say, trust carrot, it works. So if that wasn't super intuitive, you can just ignore it and just say, oh, hey, stratification good. This is how I do stratification. Thanks, Dave. All right, great. Okay, so now that we've got our folds, we need to set up Caret to use those folds to train for our cross-validation. So, as usual, we will leverage the help system and take a look at the TrainControl function from the Caret package, which is this function right here. Okay. TrainControl is super flexible and super powerful, which means, of course, that has a lot of parameters. The good news is that you don't have to necessarily become an expert in all the parameters to be productive with Caret. So we'll just focus on the ones that are most important for what we need right now, which is how do we use TrainControl to set up our training to do 10-fold cross-validation repeated 10 times. So the things that we need to really focus on are the parameters of method, number, repeats, and index. So let me just scroll down here. And we say, okay, method is just a string, and there's lots of different options, right? I can use the bootstrap, I can use the bootstrap 632 algorithm, I can just do simple cross-validation or repeated CV. That's the one we're going to use because that's what we're doing. The rest of these you can read about later. There's lots of cool stuff that Caret supports. Okay, next is the number of parameter, which is the number of folds. Okay, great. So we set that to 10, right, which also happens to be the default, but that's okay. I always like to explicitly set it because it's self-documenting code, and that's just something I like because you never know when you're going to go back to this code years later and go, what was I doing? All right, and then repeats, which is, hey, for repeated k-fold cross-validation, which is what we specified right here, right? Method is repeated CV. The number of complete sets of folds to compute. Great. So we got 10 and we got 10. Excellent. Lastly, we got to scroll down to the index function, and it's a list of elements for each resampling iteration. Each list is a vector of integers corresponding to the rows, or the indexes, used for training at that iteration. Great. So we created 100 folds, and we set that to the index. We say, look, these are our indexes we want you to use. And what this basically tells Caret all up, hey, look, I want you to train my model using repeated cross-validation. I want you to use 10 folds per iteration, and I want you to do 10 iterations. And by the way, here are 100 collections of indexes, 100 lists of the indexes to use for each of those iterations. And Caret's smart enough to use them all. So now what we've got is, ideal. 10-fold cross-validation repeated 10 times with stratified data in each of the folds. Great. Great, great, great. And we cram that into something we're going to call control 1. So we can just go ahead and run that code. And nothing shocking. Okay. Now this is where things get potentially cool depending on how geeky you like to get. So we're going to go ahead and use the DeuceNo package for multi-core training. And how DeuceNo works is that it sets up essentially child processes that are subordinate to the main thread here in R and uses sockets to connect to them. And it's a bit clunky, quite frankly, but it is what it is. It works. It ensures that you can, if you want to, you can totally just stress out your CPU on your computer to all get out, which is great because when you're starting to do some of these large scale competitions or large scale problems, lots and lots of cores is a good thing. Okay, so excuse me. And as I noted before, this works on Windows and Mac, unlike another package which is really popular in the R community, which is called DeuceMC or Do Multicore. This only works on Linux and Macintosh because it leverages a particular Unix system called Fork, which doesn't exist by default on Windows. So just use DeuceNo. It works just fine. That would be my advice. Okay, so the first thing we got to do is we have to set up a cluster, right? This is basically telling R, hey, how many sub-processes should I set up to help me do my training faster in parallel? So as always, don't hesitate. So you can just, this is the one we want here, right? It's package snow, and you make cluster, right? So you can read all about this, right? There's a whole bunch of different options. Typically, I just go with socket servers because they're the simplest, and I'm only running on essentially a single machine anyway. MPI is obviously used for like a true cluster of multiple machines. That gets to a level of complexity that is just beyond this video series. So what this code says is, look, create a cluster, and I want 6 child processes, and I want to type socket server. Now this laptop that I'm running on is a older MacBook Pro. It is a quad-core processor. It is hyper-threaded, so it can run logically 8 threads simultaneously. So what I'm essentially doing is saying, look, use 3/4 of my CPU power here, because these will be dedicated processes and they will essentially grab, in a hyper-threaded Intel CPU, they will grab one of those hyper-threads and lock onto it. So you can, if you're not careful with this parameter here, you can hose your machine. So if you're running on say a really old laptop that's like dual core and not hyper-threaded, do not set this to 6. That would be bad. Okay, now if you're running, if you've got a super awesome workstation that's maybe running like 8 cores, hyper-threaded, you could run this at 12, 14, 16 even. I wouldn't recommend anything probably higher than 14, just to give you a couple of hyper-threads available for other things. But you can see the bigger the machine you've got, the more you can run in parallel, and that's just goodness, because as you can figure out from here, we're essentially going to do 100 iterations, right? We've got 10 folds, which we know we need to do 10 runs, repeated 10 times. So if I had, for example, a cluster of size of 10, that means I should be able to conduct this in 1/10 the time than if I just had a cluster of 1. Okay, that's that. So we created the cluster object in the CL variable. We then have to register. Again, do not hesitate to invoke the help system. So what this does is basically it invokes a parallel backend on the for each package. Now why that's important is because if you just do this, Carrot will not recognize that you've set up a cluster to do work in parallel. You have to register it first. And then once you do that, Carrot's smart enough to go, oh, you want to do training in parallel? I can help you with that. Okay, so now that we've registered the cluster, let's go and register that, we can now say, okay, great, I'm ready to do my training using Carrot. So let's go ahead and do comma train, or using question mark train. And this is the actual training function from Carrot. This thing is super bad because right here tells you that you can use a single training function for a huge number of different algorithms that Carrot supports. Literally hundreds of different algorithms are supported with this common functional interface, which is just goodness. And you can go in depth and you can take a look at this for more. I would really, really super suggest buying the book. It goes into this in depth because you can do all kinds of things. You can not only train the data, but you can also do some pre-processing. So you can center and scale the data if you want. You can impute values if you want. You can do principal components analysis for dimension reduction. And you just tell it up front, and it automatically does this to all your data before it actually starts training. I mean, it's just awesome how much stuff it makes easier for you. Now, you have to understand, of course, what all this means. That's the hard part. What it does is it actually makes writing the code to do it as part of your daily activities much, much simpler once you understand all of the various bells and whistles. For example, spatial sign is a particular transform that's actually quite useful for neural networks. You probably would never use it for trees like random forest or a decision tree or anything else for that matter because you just don't need to. So that's just an example of the specialized knowledge that you need to really get the best out of Carrot. It's really powerful stuff. Okay, enough said. So one of the most important parameters to train is you have to provide a train control, right? Train control is almost like the orchestration, the brains of how you're going to do your training. In our particular case, 10-fold cross-validation repeated 10 times with stratified samples. Sweet. Second most important parameter is arguably the method. What do you want to train? This tells Carrot, use the random forest. So it's exactly the same package and function that we used in video 4. And there are many, 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 many functions, as I mentioned, that are supported by Carrot. Grows all the time. What's also interesting is that there's this thing called TuneLength. For a large number of out-of-the-box algorithms that Carrot supports, it has the ability to try various types of parameter values, hyperparameter values, for tuning. So, for example, in random forest terms, n-tree is actually a hyperparameter. It's the number of trees to use. So here we're setting it explicitly to 1,000. But there are other hyperparameter values that you can train as well, or I should say vary, on random forest. We mentioned one before in video 4 called mtry. So what TuneLength does here is it says, hey, Carrot, since you know how to do the random forest algorithm, you've got a built-in set of values that you can run over and over again using each value, a different value each time, for mtry, and find me which of those values actually works the best. And what we're saying here is try a maximum of 3 values. Now, this is really cool because it allows you to do some parameter tuning automatically, and you can just delegate it down to the machine, and it just does a grid search, and it says, look, if I fix the value of the number of trees to 1,000, I can try various values for mtry and find out which of those actually gives you the best score for your 10-fold cross-validation repeated 10 times. Now, the problem is that this is another multiplier on the amount of work that we need to do. So ostensibly, if we try 3 different values for mtry, we are now creating 3 times 1,000 times 10 times 10. Or instead of 100,000 trees, we're actually training 300,000 trees. So, as I said before, luckily for us, our trees train very fast because the data is small and we only have 3 variables. But you can see this becomes quite difficult, or actually not difficult, quite time consuming. I have literally run on my workstation here at home cross-validation jobs and competitions that I let run for a day, literally 24 hours, and I'm running my CPU at like 90%. And that's a 6-core hyper-threaded, I think it's 3.6 gigahertz. So I mean, it's not a server class box, but it's a pretty good workstation, and yeah, ran for 24 hours. So be very, very careful with this. It's quite powerful, but to quote Spider-Man, with great power comes great responsibility. Okay, so we can go ahead and run this now. And first thing we get informational warning that says, look, hey Dave, you wanted me to try 3 different values of mtry for the tune grid, but given the fact that you're only using 3 features, that's too much. I'm going to truncate it to 2, which is fine, right? It's good to know that Carrot tries to help you from doing things that are really silly. Now, just for grinsies, let's pull up Process Monitor or Activity Monitor here on my Mac, and you can see here, sure enough, right? Here's a bunch of sub-processes that are spun, and if you can hear this, you'll hear the fan on my laptop start to spin up as it's getting more and more stressed. Okay, so I'm going to go ahead and pause the video right now because there's no point in you just watching this, and then I'll resume once the training has continued, or excuse me, training has finished. Okay, as we can see here on the CPU load, training has finished. So I'm going to minimize that. I got my command prompt back again. Since I'm done with the cluster, I'm going to go ahead and shut it down using the stop cluster function. I'm not going to bother pulling up the help file for that. You can do that if you'd like. Okay, the result of my train operation got crammed into this variable that I'm calling rf.5.cv.1, right? So for the 5th random forest, this is the first cross validation run for it. And Carrot's really smart, and he can say, look, I can just invoke this on the command line, and it'll give me a nice printout. Okay, great. So, tells me it's random forest, sweet, no pre-processing, great. Resampling, hey, 10-fold repeated 10 times. Here's the summary of the sample sizes, and you can see they're about 90% of the total test set because the total test set's 891 records. And you can see here resampling across the tuning parameters. So it tried 2 values of the mtry function, and it found that on average the best accuracy is 81.09728. Now we know for a fact. Oh, sorry, I skipped over something. My bad. When we invoke the training function, I'm sorry. You'll notice here that we use the x and y parameters to say, look, use the same exact training input that we did for the RF5 random forest and use the same set of labels that we did for the RF random 5 and random forest 5, excuse me, object. So, sorry, my apologies, I should have mentioned that before I began training. So what we did was we trained 300,000 trees exactly the same way we trained the RF.5 object. Okay. And cross-validation says, look, on average, you actually didn't do as well as RF5 predicted. Remember, because RF5 predicted that our accuracy was going to be like 81.59 or 0.8159. And this says, look, no, you're a little bit worse than that. But what we know is that actually this is still too optimistic, because when we submitted our actual model to Kaggle, we actually got 0.79426 accuracy. So this is still, while not 2 points higher, it's only maybe it's 1.5-ish higher. It's still too high. And what this means, in one particular reason why this may be true is because even though I'm training with less data, I'm still training with 90% of the data. So maybe that means that 90% of the data still leads me to overfit. So another option is to repeat this cross-validation with a smaller number of folds. And what that means is that when I get a smaller number of folds, that means I actually get less data to train my algorithm on, which means I'm less prone to overfit because I got less data to work with. It also means that my test sets are actually larger, right? So for example, we could say, look, 10-fold is still too optimistic. Let's go with 5-fold cross-validation repeated 10 times. And I'm not going to drain all this code because it's basically the same. The key differences are, instead of k equals 10, we're using k equals 5. But all the code is essentially the same. Build our TrainControl object, we build our cluster, we do our training, and stop the cluster and take a look at the results. So I'm going to go ahead and run this. I'm going to pause the video again while that's going, and I will come back once it's done. All right, we're back. So we can see here that when we ran the 5-fold cross-validation, you can see that our sample sizes got smaller, so we're training with less data, but our accuracy actually got better, because right here, our best accuracy on 10-fold was 8109, and down here it is 81.2, which is an interesting result, but unfortunately not exactly what we're looking for, right? We're trying to look for something that says, look, I want it to be as close, I want the optimal mtry value for 1,000 trees to be as close to what I actually saw for my Kaggle submission as possible, right? And ideally, it would even be maybe even a little bit less, because in these types of things, we tend to want to be a little more pessimistic than not, because these values are based on us not using all of the training data. And when we actually do a model submission, we do train with all of the data, which means that there's always that little potential to overfit a little bit more. So it would be nice if our cross-validation value was actually a little bit pessimistic. But we'll see what we can do about that. Okay, so lastly, is not better. My bad. Isn't better. So let's cut and paste error. My apologies. So based on this test, 5-fold is not better. So we're going to move to 3-fold, right? And this is potentially interesting, because I'll go ahead and start this. I'll pause it when I'm done talking, but I want to talk about this just a bit while it's running. Okay, so as mentioned earlier, if you don't know anything about your data or your methodology, you know, 10-fold cross-validation repeated 10 times is a good place to start. However, what my experience has shown me, and what I've seen also mimicked by other folks' experiences, especially on the Kaggle forums, is that oftentimes a cross-validation size that roughly mimics the actual proportions of your training set versus your test set tends to work pretty well. So in our case, we know that our training set is about, you know, 2/3 of the total records, and our test set is 1/3. Or approximately, you could say, well, that's roughly equivalent to running 3-fold cross-validation, right? Because in 3-fold cross-validation, I take 1/3 of the training, hold that out, train on the 2/3, and then test on the hold out 1/3 using the model I created on the 2/3. And that proportion is relatively equal to what we see in the overall data set, which is our training set is about 2/3 of the total, and our test set is about 1/3 of the total. Oftentimes, it's not cut and dried. It doesn't work all the time, but it is a reasonable heuristic to also use as well. And what we see here is the best result that we've got out of the 3, which is, okay, our 3-fold, cross-validation repeated 10 times gives us an average accuracy of about 81%, which is the lowest of the 3 values. And while not great, it's better than our 10-fold cross-validation, right? Which, hold on, is right here. Which is 8109, and this is 8101. So, I mean, it's not a lot better, but it's probably pretty good. So, what that means is that going forward in this video series, as we're doing our feature engineering, our exploratory modeling is going to be based on 3-fold cross-validation repeated 10 times. And we're going to use that estimate of accuracy rather than just using a random forest estimate of accuracy. Now, what this also gives us too, potentially, is a methodology to use if we decide to branch out to other models. Like if we decide to use a support vector machine or an SVM, for example. We'll now know that, look, this works pretty well for random forest. It probably should work pretty well for other models as well. So this is where we'll start in terms of saying, look, hey, does this feature improve the performance of our random forests? Yes or no? Does another model type, e.g. a SVM, work better than a random forest? This is the methodology we'll use to test out that hypothesis. Okay, I think I'll stop here because this is a good logical point to stop. So cross-validation in the care package. It's like chocolate and peanut butter, better together. So learn it, live it, love it, use it. Until then, happy data sleuthing. I can't wait till the next video. Thanks.